Okay, so now we're going to work some with the derivatives of the inverse trigonometric function. So the first one here, we have 1 over the inverse sine of 2x. And so our outermost function is really just 1 over u. And the derivative of 1 over u, which is really the derivative of u to the negative first, by the power rule is just negative 1 times u to the negative 2, or just 1 over u squared. So that gives us 1 over the sine inverse of 2x, that entire quantity squared. So then we have to take the derivative of the inverse sine, and the derivative of that is 1 over the square root of 1 minus x squared, x being the input for the function. So in this case, it's going to be 1 minus 2x squared, because 2x is the input for our inverse sine function. And then we have to multiply that finally by the derivative of 2x, which is just 2. So again, we have three functions here. We have 1 over u, we have the inverse sine of v, and then we have v is equal to 2x. So in our chain, we have first the derivative of the outermost function, which is 1 over u. So that's why we have negative 1, actually this should be negative 1, over u to the negative 2, or times u to the negative 2, which is 1 over the sine inverse of 2x and that entire quantity squared, times the derivative of the inverse sine function, which is square root of 1 minus whatever's been input into that function squared, so 1 minus 2x, that quantity squared, times 2. Okay, when we work that out, we get negative 2 over the sine inverse of 2x, that entire quantity squared, times the square root of 1 minus 4x squared. And that's really all the simplification that we can do. Okay, for our next function, we have the cotangent of the square root of x squared minus 1. So our outermost function is, in this case, the trigonometric inverse function. So we'll first take the derivative of the cotangent inverse of u, which is just equal to 1 over u squared plus 1. And that ends up giving us 1 over the square root of x squared minus 1, that whole quantity squared. And that means that, and again, we have a plus 1 here. And we then multiply that by the square root of, so our second function is the square root of v, and the derivative of that, since that's just equal to v to the 1/2, the derivative of that is 1/2 v to the negative 1/2, which is just equal to 1 over 2 times the square root of v. So we end up with 1 over 2 times the square root of x squared minus 1. And that gets multiplied by the derivative of the innermost function, which is x squared, so the derivative of that is just 2x. So here we end up with 1 over x squared minus 1, when we square this, plus 1, times 2x over 2 times the square root of x squared minus 1. And that ends up giving us 2x over, and this is going to simplify to just x squared because the 1's cancel out, over 2x squared times the square root of x squared minus 1, which simplifies finally to 1 over, actually all this should be negative 1, sorry, that's the cotangent. And so we end up with negative 1 over x times the square root of x squared minus 1. Okay. So now we'll move on to our last page here, where we're talking about the derivative of a exponential function. Okay, so at what point on the graph of the function y equals 2x to the negative third, does the tangent have a slope of 21? Okay, first thing we do is we're going to find the derivative of y equals 2x to the negative 3. So we're going to have 2x. So the derivative, as you can see above, of a function a to the x is just a to the x times the natural log of a. So this will be 2 to the x times the natural log of 2. Okay. And so what we want to do is we want to see, well, where are we going to find that has a value equal to 21? So we'll set 2 to the x, natural log 2 is equal to 21. Divide both sides to get 2 to the x is equal to 21 over natural log of 2. We'll take the log of both sides, so ln of 2 to the x is equal to ln 21 over log 2. And then we get that x times natural log of 2 is equal to the natural log of 21 over the natural log of 2 equals, so then we'll get that x is equal to the natural log of 21 over natural log of 2, so the natural log of that quantity divided by the natural log of 2, and that ends up from our calculator being a value of 4.92. And when we sub that value of x into our function, this would be a calculator, you're going to end up with a y value of 28.297. So that's the point at which the tangent line will have a slope of 21. Okay, for our next dy dx for y equals x to the x. And so the hint here was to take the log of both sides. So we're going to say that y is equal to x to the x. So we'll take the log of both sides to get, let's say, ln y equals ln x to the x, or ln y is equal to x ln x. Okay, so now we take the derivative of the right side. We're going to get derivative of natural log of y is 1 over y times dy dx is equal to, using the product rule here, we're going to get 1 times natural log of x plus x times 1 over x. And we're going to end up then getting that dy dx is equal to, multiply both sides by y, and then this will simplify to natural log of x plus 1. And we already know that y is equal to x to the x, so we can replace y here with x to the x and get that dy dx is equal to x to the x times the natural log of x plus 1. And that's our final answer.